Okay, so these are some slides from QPO, which was in Buenos Aires this year. So I'll just sort of go through these, see how we go. This was a half-hour talk at QPL. So I think if I speak at a normal speed, it should be an hour talk. But please interrupt me, and then maybe we can talk about other things. I can explain other things as we go. So I'll start with ZX diagrams. So this is the language, the kind of formalism, the notation that we use for a lot of these things. So ZX diagrams are the language of this thing called the ZX calculus. Okay, and they're built out of these basic generators. Okay, so you can see these things as kind of analogous to gates, except that they're not unitary. So you can see that these are linear maps. They always have rank 2. And these things are called spiders. So there's kind of two ways to think about these. You can think of these as a kind of like a quantum gate, except that it's not unitary. Or you can think of it as like a node in a tensor network. Okay, so I can think of these ZX diagrams as a tensor net, but I've really fixed what my basic tensors are. They're just these two things, this Z spider and this X spider. Okay, and you can see that both are a generalization of a phase gate. So if these things have one leg in and one leg out, then they're a Z phase gate or an X phase gate. But it turns out it's very handy for building lots of other stuff to consider these many-legged versions of it. And then basically what that does is it kind of projects you down to the 2D space where all of these basis states are the same, and then applies a relative phase between the two vectors in that space. Okay, and that's all they do. They're not gates themselves, right? If they have more legs than one, but you can use them to build gates, and that's how you can represent circuits using ZX diagrams. Okay, so for one thing, they can represent any linear map. Okay, so not just unitaries, arbitrary linear maps on qubits. And they readily encode universal gate sets. So for instance, Clifford plus phase circuits look really nice as ZX diagrams because the C0 gate really looks quite like a C0 gate. Okay, and I can encode a universal gate set. Okay, so if I take this as you might know this as an HSH gate, so square root of X gate, and a Z alpha, then these three are of course universal for quantum computing. And you'll notice that I'll draw these things undirected quite a lot. So you notice I just put a horizontal edge between these two dots. I didn't say which is the input, which is the output. That's because these things are symmetric. So it doesn't matter, like in tensor network language, it doesn't matter if I take all the indexes up or down. It's really the same tensor. Okay, and something that's very nice about this is we have a complete set of rules. So there's about 8 equations that I can pose between little pieces of ZX diagrams. And these are complete in the sense that if I draw 2 diagrams and they represent the same linear map, then there's always a proof just by diagram rewriting that one of these things equals the other. Okay, this might not be an efficient proof. In fact, usually it's not, because we know that this is a hard problem with judging the equality of 2 circuits. But a proof always exists.
What's on the picture?
This is my dog Leela. This is the lovable slide about ZX diagrams. But then there's always a catch with these things, right? So just as my dog has 2 natures, so too do ZX diagrams. And the catch is that working with full-powered ZX diagrams, as I already said, can be exponentially hard. Okay, so if I draw 2 arbitrary random Clifford plus phase circuits, you wouldn't expect there to be an efficient way to check if those 2 things are equal, right? I wouldn't be able to efficiently rewrite one thing into the other one.
What's full powered?
So full powered here, I mean that I haven't restricted to a subset of ZX diagrams. So I allow arbitrary, in particular, I allow arbitrary phases. This phase parameter, I allow it to be any real number. So we call this the universal family of ZX diagrams. So one thing we can do to sort of look at efficient problems in ZX land is we focus on fragments of ZX diagrams. So we look at subsets of ZX diagrams where we know we have efficient algorithms. And one of the easiest ways to limit the set of diagrams is we just restrict the parameters that we're going to allow on these nodes. Okay, and so probably the most studied fragment is what's called the Clifford fragment of the ZX calculus. And this is where we restrict the parameters to be integer multiples of pi by 2. Okay, so if you think about what's the circuit analog of this, I start with Clifford plus phase circuits, so built out of say C naught, H, and Z alpha gates. And then I just restrict my Z alpha gates to be powers of S gates. Okay, so this is like Clifford circuits. Okay, so this is the ZX analog to that restriction. This is a complete set of equations for the Clifford fragment. Okay, so if I have two Clifford circuits or two Clifford ZX diagrams, I can always prove that they're equal using these 1, 2, 3, 4, 5, 6 equations. Okay, so there's always exists a rewrite from one to the other built out of these equations. Yeah.
So is this like a one-to-one correspondence as in any ZX diagram with bases multiple of pi over 2 corresponds to a Clifford operation and the other way around?
Yeah, there's a couple of ways to say this. So any ZX diagram with this restriction, where the linear map is a unitary, can be transformed efficiently into a Clifford circuit. Okay, so it's a more general tensor net, right? So things don't necessarily correspond to gates,
right?
But the unitary ones are sort of efficiently representable as Clifford circuits, and vice versa. Any Clifford circuit could be efficiently representable,
right?
This way.
And if I'm allowed to do measurements and things or like projections and computational basis states, is also because I could probably do that with these diagrams too.
Yes, that's right. So another way you can say this correspondence is any stabilizer state. So any state that's sort of characterized by a maximal stabilizer group can be efficiently represented as a Clifford ZX diagram. And then just by putting indexes up and down, I mean, any stabilizer state is kind of the same thing as a Clifford circuit with some post selections or that sort of thing. So yeah, I guess in summary, any Clifford stuff, any linear Clifford stuff can be represented as a Clifford ZX diagram.
And I guess the other way around, that if I take a diagram of this type and then I take all the X on one side, it gives me a stabilizer state.
Yes, yeah, that's right.
In this fragment, is checking equality efficient?
Yeah, so I think that's going to be what's on the next slide. Yeah, so actually, basically, yeah, thank you. Basically, anything you want to do with these things is efficient. So this is stuff that, probably starting, let's say 8 or 9 years ago, we started figuring out how to work with these things properly, and kind of in that period of time, we figured out that virtually anything that you would want to do with these things, you can do efficiently. So for instance, if there is some kind of theorem about stabilizer theory, right? So I can use stabilizers to do X efficiently. There's usually a ZX version of that theorem. So you can kind of think of ZX, or at least Clifford ZX, as the kind of tensor net analog to stabilizer theory. Okay, if I can do something with stabilizers, I can do it with ZX. Usually, if I can do something with ZX, then there is some stabilizer way to explain why this works. So this is I think a good way to think about what this fragment is like.
One small question: This yellow square is what?
Yeah. So the little yellow square is the Hadamard. It's the Hadamard gate. Yeah. So this equation is just representing the Euler decomposition of the Hadamard gate. So I can always think of it as sort of 3/4 turns in the block sphere, which is the same as rotating 180 degrees around the diagonal axis between X and Z. When I teach this, sometimes I take off my shoe and try to demonstrate that this works. That doesn't always go real well. Yeah, so you can kind of think of this fragment as like graphical stabilizer theory, stabilizer codes. Okay, so you can go even simpler. So I mean, everything was already efficient with Clifford ZX diagrams. So things will be even more efficient. Well, even more efficient, actually just as efficient from an asymptotic point of view if I restrict to what's called the phase-free ZX calculus. So now I'm restricting to where all the angles are 0. Okay, so if there's a relative phase of 0, I just don't write it on these dots. So if you see a dot which is not decorated, that just means phase 0. And this is a complete set of equations for the phase-free ZX calculus. And I guess it probably has one fewer equation than the Clifford one. And again, everything that you could possibly want to do with these things is efficient. And actually, so if you think of Clifford ZX calculus as graphical stabilizer theory, you can think of phase-free ZX calculus as graphical CSS codes. Okay, so you know how CSS codes are a bit easier to work with than stabilizer codes. Similarly, the phase-free ZX calculus is a bit easier to work with than the Clifford ZX calculus. And that's because these kinds of diagrams are very closely related to doing linear algebra over the field with two elements. And I guess lots of people here are used to working with CSS codes, and you know that the reason that they're quite easy to work with is because they're very closely connected to doing linear algebra over F2. Yeah.
Why don't we need a Hadamard rule in this?
So there is no Hadamard gate expressible in this fragment. So it's only built out of these two basic tensors. So in particular, all of your matrices will have, I think, even positive real numbers, and so you don't have the Hadamard gate here. Nothing is orthogonal, I think. So if I think about states which are +1 eigenstates of a CSS code, you know, nothing is orthogonal to anything else. So I mean, it's quite a small fragment, but it's still a useful fragment thinking about codes.
I was thinking more about, so I have two phase-free ZX diagrams that represent the same linear map. And it was not clear to me to see that they are always deformable into each other if you don't include the Hadamard.
I think I can explain the proof here, but the intuition there is that if those two diagrams are equal, then they both describe the same affine subspace. And then your rewrite rules are essentially like doing some kind of Gaussian elimination to prove that this is like one spanning set for the space and this is a different spanning set for the space. And this rule actually does a lot of work for you in proving that. Okay, so yeah, maybe I'll say a little bit more about this family of diagrams. So they're made out of spiders with alpha equals 0. And the reason that you never see a minus showing up in these matrices is that in the special case where this x dot has no relative phase, then there's another way that I can present it. So rather than as a projector onto this 2D subspace, I can think of it as a projector onto the even parity subspace of the computational basis. Okay, so this generator, it can just be thought of as summing over all the bit strings of even parity in the computational basis. Okay, and that's really where all this F2 linear structure comes from. So if I think about having this thing with, say, 2 wires in and 1 wire out, that's like the linear map that takes 2 computational basis states and adds them modulo 2. So it takes their XOR. Okay, so I think, yeah. Well, yeah, I could write it, but maybe I should move on a little bit. Okay, so one thing that you can very easily describe in this fragment is how to simplify one of these diagrams. So if I draw a big phase-free ZX diagram, I can always quite mechanically sort of squash it down to some normal form. Okay, and the way this works, so you can describe a simplification algorithm for these things, and it's pretty easy. So here are the rules that I told you are the complete set of rules. what do? I apply these four rules as much as possible. Okay, so if I have two nodes of the same color that are next to each other, I just fuse them together. So obviously that makes the diagram simpler. If I have a node with two legs, that's always equal to an identity wire, so I just get rid of it. So I just do that as much as possible. And then I apply this rule. And the easiest way to explain how to do this is I apply this rule once in a position where a Z dot, so this green dot is not an input, and this red dot is not an output. Okay, I think, yeah, so in a place where both of these things are satisfied. And what does this do? It gets all the green dots to be inputs and all the red dots to be outputs. Okay, so once I'm in that position, I won't apply this rule anymore, but I just apply this rule until I get as much as possible into that position. And then I just repeat. Okay, and what you can prove is at some point this thing is going to terminate. So these rules, I won't be able to do this step 1 and 2 anymore. And once that happens, then I say that I'm in a canonical form. Yeah.
What if you swap the step 1 and step 2? Like, what if you first arrange them so that green and red are corresponding to input and output spiders, and then you apply SP and ID?
If I arrange them.
It's the same result, isn't it? Due to the repeat.
That's why I was wondering, like.
Yeah, I think it only it's only important that you keep alternating these two
Right. Okay.
steps. So the problem is if you don't. If you just keep applying this without doing some more fusions, you won't simplify. So you'll notice that actually the left-hand side of this can be matched into the right-hand side of this. So in fact, if I don't then do some more fusions, then I don't get the property that. So what happens if I apply this rule and then I fuse as much as possible, I end up deleting two nodes. Okay, because in fact, all of these nodes are already going to be adjacent to other things of the same color. So if I do this, I'll always be deleting pairs of nodes as long as I do all these fusions. If I don't, then I can just keep applying this rule to sort of load the thing up very, very big.
But what's input and output?
Well, yeah, so you can put that in as a parameter. You can say, well, I want to call these open wires my inputs,
Oh,
and I put these as my outputs. So it's
so you pick.
you can pick, yeah. Normally you're working with something which has kind of a natural notion of input and output. So say if it's a CNOT circuit or something, then I know what are my input wires, what are my output wires. And more general things usually, so for instance, the way I like to think about it is like the input is the logical qubits and the output is the physical qubits. But it's really just convention. You can choose, and then this thing will, the normal form it ends up with will depend on how I chose inputs and outputs. Okay, so this is what a normal form will look like in the end. So I'll get all greens on the inputs and all reds on the outputs. And then I might have some internal structure. Okay, so here I have some isolated reds connected just to the inputs. I have some isolated greens connected just to the outputs. Okay, and you can actually argue that if this thing has full rank, then you'll have none of these reds. And if it has full, what would you call it, like co-rank, right? If its transpose has full rank, then you'll have none of these greens. Okay, so this represents, this kind of internal structure represents the failure of this thing to be a invertible, like a non-singular map. Yeah.
The central three dots don't represent any tensors, do they? They just represent the lines going.
That's right. Yeah.
Okay.
So you can think of this as just an adjacency matrix between the inputs and the outputs. And that's very important. So what this does is it gets rid of all of the internal stuff. So everything now is just hanging out on the boundaries. Yeah.
So the adjacency matrix represent that part, but you just said when J and K have some values, it also affect the adjacency matrix. But I thought adjacency matrix is only describing the entanglement between the input wires and output wires.
Well, yeah, I mean, so there's kind of three pieces here, right? So there's the connectivity between the inputs and outputs, and then there's the connectivity here and the connectivity here.
So what does the rank mean?
The rank, so the rank, I just mean like the rank of the matrix. So if it has full rank, I mean it's an invertible matrix. So you could say that these dots capture the failure of the matrix to be injective, and these the failure to be surjective. And in fact, we'll mostly study a case where J is 0 and K is non-zero, because that's the interesting case for thinking about encoding some logical qubits into a much higher dimensional space. Okay, so it's not surjective, and this will really capture the stabilizer structure of that stabilizer subspace. But I'll explain how that works. Okay, so yeah, let me look at some special cases. So for unitaries, J and K go to 0. So I end up just like this. And what this tells me, so this is just an adjacency matrix with zeros and ones in it. This is just the parity matrix of a C0 circuit. Okay, so for instance, like in any C0 circuit is representable as a non-singular map on a F2 linear space. So it's basically a Boolean matrix. It's telling me the linear operation I do on every computational basis state. So I can just represent that as a Boolean matrix. If I just take that Boolean matrix and put it as the adjacency matrix here, then that's the linear operator you get for C0 circuit. Another way you can say this is, well, what does a C0 circuit do? It takes some input string, x1 to xn, and every output is just some XOR of some of the inputs. Think of these red dots as XORs, and think of these green dots as copy. Okay, so it takes some bit, it copies it to some outputs, and then those at all of the outputs, it just takes the XORs of those bits. Okay, and that's really what a C0 circuit does. It's not complicated to explain the action of a C0 circuit. So in fact, if I take a C0 circuit, I can always interpret it as a ZX diagram like this. So C0 gates look like that, right? It's just like slightly harder to read for colorblind people, right? So, but it still like looks identical. We actually there's a version of the book online for people that are colorblind. So we try to think about these things.
What do you use instead of colors? Triangles and
shading. So green is white and red is gray. So
I guess that's for chalkboards.
Yeah.
Yeah.
Yeah. So the C0 circuit looks like this. If I apply that strategy that I told you about to the C0 circuit, I get something that looks like that. And that thing is just the Boolean matrix that describes what that C0 circuit does. Okay, so I've got some input bits, and at the output, I just have some XORs of those bits, and this is really just a picture of what that C0 circuit does. Yeah.
Given an arbitrary diagram of the lower form,
Mm-hmm.
Is there like a efficient way to calculate the minimum depth to compile it into just C0s? Or like how many equivalent there would be?
Minimum is difficult, right? So this is what's the status of this problem? I think this is one of those problems that people think is NP hard, but maybe they don't. Maybe they can't prove it. But there is always an efficient way to get to get a C0 circuit out of here. And the way you do it is this is basically, so I can write this as a matrix, and I can write C0s as primitive row operations, like elementary matrices. So it's always a single C0 is like an identity matrix, and I put a 1 in sort of the row of the control and the column of the target, right? And you know that if I have any matrix, I can do Gaussian elimination. If it's an invertible matrix, I can turn it all the way to the identity matrix. That's the same thing as decomposing an arbitrary matrix as primitive row operations or C0 gates. So this is like if you know about there's C0 synthesis algorithms like Patel, Markov, Hayes. They use this fact to synthesize circuits from or to resynthesize circuits. So you can compute the parity matrix and then you can sort of resynthesize it. And there are good heuristics for doing this in low depth or for low gate count. and stuff, but. Finding the exact optimal, I think you need to try all of the row operations. So you can pose this. As it is an NP problem, you can ask, does there exist a composition of this depth? If you just give it to me, I can check if it's a good one, but it's, yeah, I think it's hard.
Thanks.
Cool, 45 minutes, I'm about a third of the way through, so this is actually the speed that this talk should be given. But yeah, we'll see how far we get. Yeah, so you can, these normal forms, you can just write it as a parity matrix like this. And this is really just describing what the unitary does to the computational basis states. Okay, so this is what I said before. A much more interesting special case is isometries. Okay, so let's take let's take one of these normal forms, but I'm going to assume that the linear map is an isometry. Okay, and in fact, it's enough to assume that it's injective, because all injective phase-free ZX diagrams will be isometries. Okay, so this is kind of like, with Clifford maps and things, like everything tends to be unitary or isometry as soon as it has a big enough rank. It's kind of like how everything either is orthogonal or sort of is unbiased, like perfectly overlaps in Clifford land. So if it's an isometry, then it has to be the case that there's none of these red dots at the input. So I've only got some green dots at the inputs, and I've got some isolated green dots. Okay, and then some outputs. And what is this thing? Well, again, I can now label my inputs with some variables. I can also label these isolated things with some variables, but it's a different kind of thing, right? Because it's not an input state, it's a different kind of thing. And then I can write these parities as my outputs. And what does this mean? It means that this isometry is describable in this kind of way.
I forgot what an isometry is. I know planar isometries.
Okay, so an isometry is like a one-sided unitary. It's if I take a matrix and I compose it with its adjoint, that's the identity, but not the other way.
It's unitary embedding in the large.
Yeah, exactly.
Yeah. Unitary embedding is maybe what some people, or an isometric embedding or something. So
like if your output of the unitary, you just is a subspace of a larger space.
Then it's
Isometry. Because it preserves lengths and angles.
So all it needs, formally all it needs to do is preserve the inner product, because then that implies that it has a trivial null space.
Okay.
And it also implies that if I now apply the adjoint to the thing, I'll get back to the vector that I started with. Yeah.
Okay, I have a question to the slide before that you just showed. Yes, no, the one after, where it's explained that there's an isometry also for k equal to 0. For m equal to n, because then both spaces have the same size, but the k makes somehow shrink the image of the map, doesn't it?
So being an isometry implies this stuff, right? Sorry. It's not an equivalent. Yeah. So also also in the unitary case, because this matrix needs to have full rank as well, right? So being a unitary, you could beef this up to an if and only if, and I think it's the fact that
maybe the n minus m equals to k or something like this.
It's I think if it's something like, if I make a block matrix of these two parts, then I think that should have full rank or something like that. It's like saying that these green dots don't sort of cancel your space and right in a certain kind of way, something like that. But anyway, yeah. So the implication goes one direction, not both directions. Yes.
So here about the full rank, can I understand that you have a matrix where you have 4 rows, and then you have 4 columns where 4 rows correspond to x0, x1, y0, y1, and then the 4 columns correspond to the red spiders.
Yeah, yeah, I think that's up to whether that's whether it's that or swapping rows and columns. I think that's the correct thing.
Actually, could
Yeah.
we go back to the previous slides? Because earlier when no, the next one. Yeah, earlier when I look at this, I got confused about, given this diagram, how do you describe the parity matrix of this diagram? Is it that you treat the green spider without input as also like a spider so that you?
I'm about to explain that.
Okay.
Okay. Yeah, so yeah, what linear operator does this thing correspond to? So it generalizes the unitary case. I have two kinds of variables now. I have these input variables. I also have these non-input variables. Okay, and then I have two adjacency matrices that describe them. Okay, so now I'm somewhat sort of evocatively calling these L and S for logical and stabilizer. Okay, so this isometry will take an input bit string and map it to now a sum over output bit strings. And it's going to be the L applied to X plus summing over all Y of the S applied to X. Okay, so if people know CSS codes, these are the code words of a CSS code. Okay, so if I take any bit string and I apply some fixed L to it, and then I sum over all the bit strings applied to my stabilizer matrix, then this gives me a code word. Okay. And yeah, saying that all of that I've chosen a kind of a minimal set of stabilizers and also that I have a kind of a full set of logical operators is saying that all of these 4 columns are linearly independent. And that would give sufficient conditions for this thing itself to be an isometry. Okay, so in some sense, yeah, that's kind of equivalent to saying that this thing is an isometry. Yeah.
In the simplification step that you explained maybe 5 minutes ago or so, I would have expected this linear independence to be automatically given, because if not, you could apply some further rules to it. So reduce the number of green dots.
Yeah, so
that carry this.
So say for
that label.
For instance, if I have something which is given to me as a C0 circuit plus some ancilly prepared in this is phase free, so my ancilly can only be in the 0 state or the plus state. So this is like a CSS code encoder circuit. If I apply this simplification procedure, then I will always get an isometry. Well, I mean, I know this thing is an isometry because I gave you an isometry when I started. So I'm about to sneeze. No, I'm not. It could be the case that these S's are not independent by the time you terminate with each other. I could have redundant stabilizers, but then there's some further rules where you can do Gaussian elimination between these stabilizers to get these to be independent as well.
To be clear, if you follow the algorithm to simplify that you show, even on this diagram that would have redundant green spiders, you would be of a form where the algorithm would terminate.
Yeah, so you could terminate with some redundant stabilizers.
Yeah.
I mean, I could describe you a slightly fancier algorithm where the next thing you would do is just get rid of some of the redundant stabilizers.
I see. Okay, so you would need to do this.
Then
clean up.
Then you can do this kind of tidy up. So there's another rule which says basically, if I have 2 dots like this, I can effectively add one of these dots to the other one. So I can add its connectivity, which is like taking a column of this matrix and adding it to another column, which I could use this to set some dependent column to 0.
Yeah.
And then that kind of tidies up. Yeah.
So is there an easy way to see that this stabilizer, like this matrix that comes from the stabilizers, have like an X part and C part?
So this is which is it? This is just the X part. Okay, so with a CSS code, one way I can give you fully specify the CSS code is I can only give you the X part, or I can only give you the Z part. So if I give you just the X logicals and the X stabilizers, that's enough to compute the Z logicals and the Z stabilizers. So normally you might want all of this data. Or you could just give me the X stabilizers and the Z stabilizers, and then from that compute the logicals, right? So, but it's redundant data. There's kind of more than you need. And in fact, I think I'll explain the yeah. So,
But out of curiosity, when you say you apply the algorithm, right? Like you gave us the algorithm in terms of this diagram, but you keep referring to the matrix representation. So what do you really do? Like, do you go to the matrix representation and you do linear? You mentioned column, Gaussian elimination, and then understand that you can write a parity check or binary matrix, but
you can do both. I mean, so I think there's useful ways to think about it in both ways. So thinking about it as doing linear algebra, but you can really just apply graphical rules. So I can give you this graph and I say, well, here's this graph rewriting strategy, just apply it until it terminates. And then what that will secretly be doing is it's applying some Gaussian elimination on some matrices. Is that how you would want to do it necessarily? No, not really. But this is explaining, how this particular graph rewrite system behaves, as you can understand it in terms of Gaussian elimination or something. So I was saying that this is the X part. So this gives you the X stabilizers and the X logicals. ZX, everything in ZX is color symmetric, right? So I could describe you the exact same algorithm, but just reverse the role of red and green and just apply it, and I'll get another normal form. The graph will be different. I'll have red dots on the inputs and green dots on the outputs. That will give me the Z logical operators, the Z stabilizers. Okay, so a typical way that you work with these things is you always have two dual forms to each other, and you can kind of flip back and forth between them. So this is the X biased representation. Okay, so if I want to know something about the X side of my CSS code, I'll use this representation. Or I can flip to the other one and say, I want to know something about my Z stabilizers and logicals. I'll flip to the other representation. And they're always linear algebraic perps of one another, right? So they're kind of orthogonal in a certain sense to one another, in the same way that in CSS codes, the subspaces are orthogonal to each other. Okay, so this is this year's work, and something that we wanted to try to understand was kind of going beyond Clifford's. Okay, so now Clifford rewriting in ZX is very well understood. We know that arbitrary unitaries or arbitrary linear maps are going to be hard. We expect them to be hard, like QMA hard kind of problems and stuff. So we were wondering, is there any non-Clifford stuff that we can handle in useful ways with the ZX calculus? And we already kind of know that because we've been using ZX to do things like reduce the T count and Clifford plus T circuits and this kind of stuff for a long time. So we're trying to kind of understand some of the non-Clifford structure of these things. And one thing that is non-Clifford, but is still you can still kind of work with, is I wouldn't say fully tractable because you can pose hard problems here, but certainly has a lot of algebraic structure, are the diagonal non-Cliffords. So if you know about like the Clifford hierarchy, the diagonal third level of the Clifford hierarchy are basically the gates that I can build with C naught and T. Okay, and then the diagonal ones of those, right? So maybe I prepare a bunch of complicated parities, I do T gates on those parities, and then maybe I sort of uncompute them or something. Already because I described it that way, you can tell that there's some structure to these circuits. I can always think of it as something where I've done this.
So a stupid question, T gate is Toffoli gate?
Yeah, I realized that there's like specialized terminology here. So a T gate is a is a square root of a S gate. It's a Z phase by pi by 4.
Mhm.
Okay, so it's a square root of the first Clifford Z phase. Okay, so it's a non-Clifford thing, and it's kind of the most obvious sort of next gate that I might want to take. The sort of non-Clifford gate. And Clifford plus T is approximately universal. So I can approximate any unitary to arbitrary precision using Clifford plus T gate. So it's sort of interesting for universal computation.
Thanks.
Okay, so in the graphical picture, the diagonal non-Clifford gates are all generated by these things. Okay, so we call this particular kind of diagram, we call this a phase gadget. Okay, so this is a unitary map. And what does it do? Well, it takes in a computational basis state and it applies a relative phase between the parity 0 subspace and the parity 1 subspace. Okay, so if all of these bit strings sum to 1, I'll apply a phase. And if they sum to 0, I won't apply a phase. Okay.
So like multi-control C gate or like phase gate.
So you can build a multi-controlled phase gate out of these things. In sort of a more physics way of thinking about it, it's an e to the I alpha z z z z gate. It's like an exponentiated z gate. Ising interaction, I guess, is what the physicists call these kinds of things. Yeah. You're like, maybe.
If n is 2.
Oh, if n is 2. Okay, yeah. So a multi-qubit phasing yeah, not an Ising interaction. But yeah, you can think of it as a exponential of a Pauli. And if I have these things and if I have local Clifford gates, then this is universal. Okay, so I can sort of build everything out of sort of a sequence of exponentials of Pauli strings. And this is, like, for instance, when people do universal computation in the surface code, this is one of the ways you might think about it as I decompose my circuit. Basically, where all my multi-qubit things look like this up to a local change of basis or something.
So, but you're saying like, do you know this IQP setting where you allow preparation and plus measurement?
Yeah.
Is that in this
Yeah.
work you're allowing? Okay.
Yeah. So this is if you think about what the unitary part of an IQP circuit is, it's generated by things like this.
Right.
In fact, this is exactly the things it generates. So if I put this alpha to any non-Clifford thing, then this is still a hard problem. So computing like IQP probabilities plus basis, this is still hard.
Got it.
But it becomes trivial if I take the computation basis in the inputs and outputs, because in fact it just
goes right there.
Yeah, it always acts trivially on the 0 state, and it always acts the same way on the parity 1 state.
So you said that you can, if you take the diagram, exactly what's on the left, pi over 4, you can combine these together with a phase 3 part, I guess, to approximate any.
You need the Clifford part. So
the whole Clifford.
Yeah, so you need H. I think you just need to add H gates.
Yeah. Is something known
because S is already included there, but
is something known about the size? So say I want to compile a alpha rotation in terms of these pi over 4 things. Is there something known how this minimum size of the network of this compiled network behaves with alpha? So say if alpha is not a fraction of pi.
Yeah,
I would expect this to be.
So it's the question becomes harder the more qubits you consider.
Yeah.
But for single qubit rotations, this is very well understood now. So you can really compute so I give you a rotation and I give you an error parameter. So how close do I want to approximate that rotation? And there's an efficient algorithm which will synthesize the shortest out of the shortest number of H and T gates. How do I approximate that thing? So I mean the kind of original algorithm for this was like Solovay-Kitaev kind of thing. But now there's better ways to do it with using some number theory where you can actually get the exact optimal amount. So this is Selinger-Ross result from 2015.
15.
Oh, that's late. That's later than I thought. I was going to say like around 2006, but yeah, it's relatively recent.
And if you don't care that it's a circuit, just the ZX diagram.
Oh, that's an interesting question. I don't know if anyone's ever thought about that. So that to make the smallest non-Clifford circuit that approximates some arbitrary, say a random state or something like that.
Or say I want to implement kth level Clifford. Like you can
Up to
put
epsilon,
some, yeah, I don't know, put some restrictions. I'm not saying that general, but maybe
Mm-hmm.
for some, like, yeah, maybe there is a qualitative difference.
Yeah, I mean, I think the generic ZX diagram problem, you can probably always map this onto some sort of state preparation problem. So say I give you like a random in-qubit state, and I want to find the smallest Clifford plus T state preparation circuit for that. I think up to a constant overhead, that's going to be the same size as the smallest ZX diagram that builds the thing. Something like that. And I would expect people have thought about that problem. They probably haven't thought about the ZX problem, they probably thought about the circuit problem.
Okay, yeah, that helps.
Yeah, so it's been an hour now, so if people have to go, you can tell I'm less than halfway through the slides that I have, but this is fine. I would rather people understand things than get all the way to the end.
So far.
You share the slides.
Yeah, I'll share the slides.
Looking forward to it.
And I guess there'll be the video that you can watch at double speed later as well.
Just
You have a hard limit of half stop, I would say.
Okay, because that's lunchtime.
I think, well, unless people are willing to go hungry, but that's when people will start getting crabby with it.
Okay.
you get angry faces.
Angry faces. Okay, yeah, okay. Well, let's see here. Yeah, I probably won't linger too much longer, so I might kind of jump to what the cool stuff is. Okay, so yeah, these phase gadgets are interesting because you can very easily capture the diagonal Clifford hierarchy. Okay, so if I want D3 unitaries, then I put pi by 4s on here. If I want DN unitaries, then I put pi over 2 to the n minus numbers. So if I just put smaller and smaller angles, I sort of just climb the Clifford hierarchy as high as I like. And there's a simple way that I can use ZX calculus to do, say, T-count optimization for circuits. And one way to do this is I use sort of my Clifford ZX calculus to simplify as much as possible. And sometimes what will happen is I will get these phase gadgets appearing. And when they appear on the exact same subset of my qubits, I can just fuse them. Okay, so if I look at like the form of this diagonal gate, clearly if I get 2 of these things happening with an alpha and with a beta right after each other, then I can just put alpha plus beta together. Okay. And now if both of those things were pi by 4, they'll fuse to make a pi by 2. Pi by 2 is a Clifford thing, so then I know how to reduce it farther. Okay, so that reduces the T count if I do this kind of thing. And of course, if it's a pi by 4 and a minus pi by 4, they'll just cancel out. Okay, so for instance, I can take this thing. So this is a C0 plus phase circuit. I can pull the phases out. This is using that fusion rule backwards. And then I can use my phase-free normalization. And I'll always get something that looks like this. So basically what's happened is it's treated all of my non-Clifford stuff as just more outputs to my matrix. Okay, so now I've got a phase-free diagram, and then I've got 4 extra outputs. And then I just apply the simplification that I already knew from phase-free diagrams. I get something like this. And then I can do this gadget fusion rule And I get, I can start to eliminate things. And what you'll notice is in my original circuit, this alpha and this gamma parameter are far from each other. Okay, so it's not like I just found two phase gates next to each other and I added their phases together. I did something a bit more non-trivial here. So I really used some structure that was hiding in the circuit. And people already knew about this kind of thing. So they would use what are called phase polynomials. So I can efficiently evaluate the phase polynomial of a Clifford plus phase circuit. And I can use that structure to do these same kinds of non-local jumps. So again, this is just what that looks like graphically. And then, yeah, I can sort of turn it back into a circuit and you see that I've got one less parameter.
Do you have an easy way to see that a control Clifford gives you a level more in that?
What's the best way to see that? I mean, so there's whenever we have a gate, there's a way that we can construct the controlled version of the gate, but it's very similar to how you would do it with circuits as well. Like if I have a unitary, I can sort of decompose it and I can control all the gates in there.
Yeah.
And this process of controlling things divides all the angles inside by 2. And yeah, I guess that's one way that you can see how you kind of climb the hierarchy. The nice thing about these phase gadgets is adding more qubits to a phase gadget actually doesn't climb the hierarchy. But that's not the same thing as a multi-controlled gate where I have to actually do a phase gadget by alpha over 2 and then sort of correct by alpha over 2 on all the control wires. And then yeah, you'll see that kind of climbs the hierarchy by 1. But usually for diagonal Clifford hierarchy things are easy, and then for more generic Clifford hierarchy things, it's harder to solve these kinds of problems, I would say. Okay, so for general phase gates, this is pretty much the whole story. So this is as much. If I treat my non-Clifford angles as black boxes, this is kind of the most I can do in terms of reducing circuits, so optimizing circuits is this kind of gadget fusion thing. In fact, you can prove that this strategy is optimal under this assumption that I'm treating my angles as black boxes. Okay, so this is a very restrictive setting where I'm not using the fact that I knew that these were actually T gates. But if I know these are T gates, in fact, if there are any pi over 2 to the k gates, there's many more non-Clifford rules that apply. So for instance, here's one, which looks like some sort of alien spaceship. This is not quite as nasty as it looks from the graph. So what's happened here is I've taken 4 wires and I've put a phase gadget on every subset of those 4 wires. Okay, so every non-empty subset, I've put a phase gadget on. So there's 15 here. So 2 to the 4 minus 1 phase gadgets over here. And then it happens to be that when you do this, it's very fine-tuned. They all cancel out with each other, and I'm left with the identity. Okay, so this is a very non-trivial, very non-Clifford phenomenon that happens specifically with T gates.
Tangential, but why do you prefer to draw these spider nests like this as a big nest? Why not each phase gadget one after the other so you can really see which wires that?
Well, you can. Yeah, I could unfuse this. I could unfuse this thing and I could see it like this and yeah, I think both pictures are useful.
Okay.
I think this picture is very beautiful, but it's not particularly informative, right? And in fact, this is drawing these pictures by hand is not a good way to work with these things, in fact. And in fact, I think that's probably sort of getting to where I'm going to end, which is how we actually work with these things, which is not drawing these big, nasty graphs of these things.
Why the summation of all of these terms would cancel out with each other and then give you identity?
That's a good question. I'll explain.
Oh, okay.
So well, I don't know. I don't know if I've got it in slides, but I can explain it, but it's not intuitive, I think. So it has to do with the way that the Fourier transform behaves. So yeah, the question we started asking is, can we classify all of these really complicated identities and work with them in an effective way? And it turns out that we can, but working with them as these big nasty ZX diagrams is not a nice way to work with them. So we use this thing called scalable notation. So scalable notation is where if I have, rather than writing single qubits, I actually write registers of qubits. Okay, so here I've got something from 4 to 3, and it's got some connectivity like that. I'll just write it like this. Okay, so now I've got a register of 4 qubits. So I've got 3 qubits out, and I've labeled this thing by its connectivity. So I've just literally put this matrix on here. Okay, so now this is somewhere in between doing linear algebra and doing graphical stuff. I kind of have both things here. I've got diagrams labeled by matrices. And these arrows, yeah, so I can do the same thing with spiders. So rather than having a bunch of wires, I can also have a bunch of spiders. And then I have this arrow thing for this connectivity. Okay, so this is like, I have a bunch of green spiders connected according to this adjacency matrix to a bunch of red spiders. And these satisfy a bunch of very nice rules. Okay, so in particular, if these matrices come together on a wire, they multiply. They copy this way through green. So they sort of copy forward through green. And they copy backwards through red. Okay, so I can sort of pull one of these wires backwards through a red dot. I can push it forward through a green dot. And I can also decompose block matrices this way. In fact, you can almost take this as an inductive definition of what the arrow is. Right, so I can think of this as I pull apart the matrix until I get all the way to the bottom, and I have a 1 by 1 matrix. It's a 0 or a 1. A 0 is going to break the wire by sort of a green dot, and then no wire, and then a red dot. And then a 1 is just the identity. And all the spider nest identities now look like this, okay? But not for any matrix. This M needs to be a triorthogonal matrix. Okay, so if people know about magic state distillation or transversal T-gates or something, you see these things coming up. These are Boolean matrices which satisfy these triorthogonality conditions. Okay, so we work with columns rather than rows, but normally you see it with rows in literature. Every row needs to be 0 mod 8. Every dot product of a pair of rows needs to be 0 mod 4, and every triple of rows, so that's why triorthogonal needs to be 0 mod 2. Okay, and in fact, you can show that this kind of diagram equals the identity if and only if this thing is a triorthogonal matrix. And the way that you can prove this is like I kind of mentioned briefly. You take all of these phase gadgets, you take their Fourier transform, and then you can prove sort of in this Fourier basis that the thing is going to be identity exactly when these are satisfied. Okay, so it's really it's capturing a lot of structure there, but it's really non-trivial, big scalable structure.
Do you have so if I would not use pi over 4, but what's the next one, pi over 8, I guess? Is there similar conditions on matrices such that this identity?
Yeah, it keeps going up. So
like
say, yeah, so you can describe what L orthogonal is, which is always here. This top row is going to be 2 to the L minus 1. So for the third level of the Clifford hierarchy. Oh no, I guess it's 2 to the L. It's 2 to the L here. So for the third level, it's going to be 8, 4, and then 2 down to triples of rows. But then for higher and higher, I just need to take more and more products of rows until I get all the way down to 0 mod 2. But yeah, everything here works exactly the same way as you climb the Clifford hierarchy. You just need to do more.
Do you have intuition why it's always a power of 2 instead of a power of something else?
Why is it powers of 2? It's because when you take the Fourier transform of these things, you're doing it with respect to the abelian group, which is like Z2 times Z2 times Z2 times Z2 times Z2, something. So that's why you get this power of 2 structure. I imagine if you did this over Q trits or something like that, then it'd be a power of 3 thing. So I think it comes from the qubit dimension.
Oh, okay. Thanks.
Sorry, you mentioned the Fourier transform a couple times. Where does the Fourier transform come in? I think I missed it.
Yeah, I get so it's you can think of like if I have a bunch of phase gadgets, I can think of the angles labeling these things as the Fourier coefficients of a what's it called, a quasi-Boolean function, so a function from bits to real numbers. And I can think of this thing 2 ways. I can think of it with the Fourier coefficients, or I can think of it with the kind of Dirac delta coefficients. And then the way that I relate these 2 things is I do a Fourier transform. It's actually it's a finite it's a discrete Fourier transform, but yeah, that's where this is. That's what's hiding in there.
Okay.
Yeah, I should wrap up before there's much hanger. So I think I'll skip this part. So there's a way that you can show that if I just put one of these rules in, it implies all the other rules. And yeah, there's some inductive arguments you can use graphically. It's all very nice. You can ask me about it. But I think the more interesting thing is thinking about transversal gates and magic state distillation now that we have these extra rules. So I've already mentioned this a few times that we can think about encoder maps as something with some K logical wires coming in and in physical wires coming out. And the image of this map is a stabilizer code. So if I draw this thing as a Clifford diagram, its image is going to be a stabilizer code. So for instance, here I have one of these phase-free isometries. The image of this is going to be a CSS code, or I can think of this as the sort of encoding map of the CSS code. And the X logical operators are given by this matrix. The X stabilizers are given by this matrix. So what I can actually do is write this in scalable notation now. Okay, so I just put my logical matrix here, and I just put my stabilizers there. Okay, so now I have a scalable picture of this matrix. And if I want to know what is transversal for this code, so say I want to know what are the things that I can implement inside this code with a transversal T. So I can apply a power of T now to every physical qubit. What kind of logical operator can I get there? That's like saying, if I start with this thing, which is let's say that this P is well, you could say, take P to be the identity matrix, and then that's just applying T on every single qubit. But I could also have repeated rows in my identity matrix. That's like applying powers of T to my qubits. What sorts of these things can I kind of pull backwards through the encoder to put on my logical space? So what preserves the logical space, and particularly what acts non-trivially on the logical space that I can implement transversally on the physical side? And in fact, what you can do is, using these scalable ZX rules, I can take these transversal T's and I can pull them back to the logical side graphically. Looks like this. Okay, so I take it over to this side. What ends up over here is a kind of a block matrix that looks like this. Okay, so this is a little bit fast. But the point here is that I want this side to equal this side, which is equivalent to saying that this part of my diagram vanishes. And we know that that's equivalent to saying that this matrix is triorthogonal. Okay, so what does this say? this implements a D3 operator described by H. If and only if this matrix M is triorthogonal. Okay, yeah, that's kind of, it's a, because this is stated a bit generically, so this isn't just for transversal T, this is for any powers of T. But now I can tell you, this is a recipe for checking if my code has a triorthogonal, has a transversal implementation of a gate. So I tell you the phase gadgets that implement that gate. Okay, so maybe it's a T gate, that's just a single phase gadget. Maybe it's a CCZ gate, that's like 7 phase gadgets. So I tell you this H, this is the gate I want. I tell you my logicals and my stabilizers. And then if there exists some P to make this thing triorthogonal, then I know I have a transversal implementation of this gate. Okay. And if you look at these characterization theorems, they're quite hairy. Like, I think this is one of the nicest way to actually say this, even though it is still a bit, it's a bit windy.
Your like permutation matrices, P is the same for logical stabilizers.
Yes.
What are the constraints on P, I think?
So P, I think each of its rows needs to be a unit vector. So it's like an identity matrix, but I'm allowed to have repeated rows or omitted rows. So
Okay.
if P is the identity, that's like saying do a T gate on every single physical qubit.
Okay, it's that one, okay.
Yeah. And in fact, if you, yeah, how does this work? So if you take P to be the identity, and you take H, I think also to be the identity. So that means implement T gates on all of my logical qubits.
With T gates on all of your physical.
Yeah. Then this matrix M is triorthogonal exactly when you have what's usually called a triorthogonal code, like in Bravi and Ha or something. So this condition is, I think they call this something like a generalized triorthogonal code. So these are the things which implement, say, transversal CCZs or transversal controlled S or that sort of thing. Yeah.
What's the 0 and why don't you just omit the wire?
Yeah, so I guess, so I put the wire in here. So here the wire is omitted.
Yeah.
Yeah, I put the wire in here so that I can sort of pack it all into one matrix like that. So that you can say it as a matrix condition. And I think, yeah, so here's the theorem you could say, right? So this sort of puts it all together. I have a transversal implementation of this thing, if and only if there exists P doing that. Okay, so a couple of examples of this. So this is the 1513 Reed-Muller code that people use for magic state distillation. Up here, I can read that my one logical qubit has a T gate on it. And this is actually the sort of the stabilizers and logicals of this code. I think actually you should read it this way because it's transposed. Anyway. Another example is this is the 832, which is sometimes called the smallest interesting color code. There's this blog by Earl Campbell that is like quite famous about this. But it shows that this, even though this is only an 8-qubit code, it's actually got a transversal CCZ, which is quite nice because then I can use that to do magic state distillation in a different kind of way using catalysis and these kinds of things.
So you will handle transversal unitary non-Cliffords, but
yes,
there are also codes in which say Clifford measurements are transversal. So is there an easy way to see this?
Oh, that's interesting. We haven't thought about
if you have
transversal measurement.
If you have a transversal CZ, for example, you can measure just physically the CZ, and you will have measured the logical CZ. So, but yeah, I don't know if it's like a sufficient, if it's a necessary condition to have a transversal Clifford such to problem, or if you cannot use matrix. But
I think that's the kind of question you could probably answer pretty easily in this kind of formalism, because we also have representations of measurements in this language. And And you can certainly see, for instance, that, I can always measure my logicals transversely and that, I can do Pauli measurements fault tolerantly by measuring all of my output qubits and these kinds of things. So it'd be interesting to think about more general, like these. I've never thought about Clifford measurements before, but I guess that's an interesting thing.
You have to be a bit more clever with decoding, but we know how to do it in time fashion, at least for a certain class of codes.
Interesting. Maybe you can show me this afternoon or something.
Yeah, sure.
That would be cool. Yeah. So here's a transversal CCZ. The thing you notice is these are the phase gadgets of a CCZ. So it's like, if you know about circuit decompositions, I need 7 T gates to make a CCZ. These are like the 7 different parities that I need to put a pi/4 phase on. And then these are the X stabilizers and logicals of this color code. So you kind of see all of the transversal structure kind of packed into this matrix or packed into this picture, if you like. And this is all explained much more carefully in the book, by the way, so if you want to grab the book. So yeah, I guess the scalable notation is, I think, the right way of working with these things, because I mean, a criticism we got for years is like, well, yeah, if you want to do anything non-trivial, you're going to have big, nasty graphs, and I agree with that. So you have to, it shouldn't be fully graphical, right? But I think mixing the graphical and non-graphical techniques is a really powerful way to work with these things. And yes, so these are just some open questions. So basically, can we use this to do useful new stuff? Okay, so this is all existing stuff, or taking existing things and making it a bit nicer. So finding equivalent ways to say things in nicer ways. But can we find new stuff? And I really expect we can, like for instance, like this stuff that T is doing with Pauli webs and flip-kedifying codes and stuff is all, I think that's quite exciting. But I think there's a few different directions where you can find some really genuinely new fault tolerant techniques using this stuff. So I think that's a good place to finish. So yeah, thanks everyone.
Everything's great. Do people want to follow up questions? Have you got any questions, or do people want to get away?
I have 2 questions.
Yeah, I've got some questions.
The first question is, if you
But
go
if
back.
people want to leave, head to lunch now, feel free.
Oh, if you go back 1 slide. So in the example here, just now you said P can be having 2 rows that have 2 identical rows, meaning that P could be not full rank, right? It's like.
Yeah, that's right. So that having an identical row corresponds to putting 2 copies of the same phase gadget. So it's like putting rather than just having a T gate on one of my wires, it's like having a T squared or a T cubed or something.
Oh, that's actually my question. Yeah. So I was like, what does it correspond to, like that right-hand side?
Yeah, and if you omit a row, that means I'm actually just not doing a T gate on that phase gadget. You can also do this. So this covers cases where maybe I just do T on some subset of my physical qubits rather than on every single one, which is also fault tolerant. So.
And another question is, so you said about the application, and we know that if you input different non-stabilizer state, you could use the state injection protocol to realize non-Clifford gate. And could this ZX like visualization help to prove this? Because the previous question, so we were at like a compilation workshop, and people asked, could you realize any non-Clifford gate? And then somebody said, oh, you could use magic state injection. So I wonder if this has any connection to proving such things.
I mean, you can very nicely write various kinds of state injection protocols using the scalable notation, because a lot of times things that would just be doing something on a single physical qubit correspond to doing that thing transversally on many qubits. So you can prove, like, yeah, you can write down state injection. Yeah, I don't know if you learn new stuff about that, but I think it's a nice way to think about it and sort of write down, prove that it works and everything. So
this brings me to thought that it's like, so if you think of injecting a magic state into a 2D color code from a 3D color code, it's possible to only do an operation on a subset of the physical qubits of the 3D color code. And then, right, so and the reason for that is that actually like the 3D color code has like a 2D color code state living on its boundary. So you kind of just measure out half of the qubits after having applied the transversal T. So can you here also, you assume like kind of transversal operations? As far as I understood, is there an easy way to see this if such an operation is possible to also only act on a subset of qubits?
So you could, there might be a nice way to say this with block matrices, where you're you use this kind of arrow notation.
Yeah.
And for instance, so if I, I don't know how exactly to do this with like a lattice surgery or something, but I would imagine like I can sort of split my qubits into kind of a bulk and one of the boundaries or something.
Yeah, that's the easy example, I guess.
And then do something that's like it only has support on like on the boundary part of the matrix, and the rest is 0. So you could, I think you could write this like if all the, so it's all, it's still all qubit codes, right? It's still just different amounts of physical qubits, right?
Okay, so this would then just enter some conditions between SL and this H, I guess, to result in a certain P. Right, you were saying that the matrix.
Yeah, you could sort of decompose these matrices, or you could split the encoder into multiple wires. So rather than thinking of it as just one register where I put all my physical qubits, I can sort of I can sort of peel it off and I don't want to take too long here. But maybe I can show you a picture that's sort of interesting here. So in the scalable notation, there's a way I can sort of peel off some wires from a register and say, do some stuff only to these wires. So we've got these kind of peel apart and put back together type of generators. So probably what you would want to do is you have like the 3D code, and I'm going to peel off a boundary and then do something between the boundary and the other code. And then maybe once I'm done, it can rejoin, or maybe I don't care what happens to those qubits after or something like that.
Yeah, but if you don't know the two codes from the beginning, it's difficult to see whether you are having a distance or Maybe you can see that you can kill some qubits in this way, but you don't know if you don't start with the right one at the beginning whether you kill like all the distance or probably your boundary that is a good code or something useful.
I think you need some.
You don't have that.
You need some extra reasoning, I think. So it's probably. I mean, this is all things that you could kind of say in terms of the matrices. Yeah. Right. So I think you can use the pictures to describe the protocol, but ultimately, this is a high level picture of what's going on, and then there's some reason you'll need to do some reasoning, maybe some like homological reasoning or something about the structure of the matrices that I'm sort of pulling apart or something. So Aleks Kissinger, who's a PhD student of mine in Oxford, has been thinking a lot about doing surgeries between different kinds of codes. Thinking about it kind of in the category of cell complexes or chain complexes, and they're giving some sufficient conditions for when I glue a logical from one code into a sufficiently similarly shaped logical of another code. So, but it's not at all pictorial stuff. But you can imagine like using that to think about what's happening at the code level, and then using the pictures to design protocols around those properties or something like that. Maybe.
I have questions about the conditions on P, like. So your definition of transversal, and maybe I just don't know the definition of transversal, it's like it needs to be single qubits. It powers of T on single qubits.
Yeah, so this was inside of one code block. You could also have multiple code blocks.
Yeah.
And then your matrix P satisfies a sort of an analogous condition, which is it's of the form of a sort of a block matrix QQQ to how many blocks you have. And each of those Qs needs to have the same condition that the P had. And that's like saying I'm only interacting the jth qubit with the jth qubit in every code block.
Right. Would it be so bad? So if I had a bunch of qubits and rather than only restricting myself to applying powers of T on single qubits, if I just wanted to have everything done in one time step, but I'm allowed CSs and CCZs and stuff, is this still of interest? Like, if I can do it transversely, but I'm not doing single qubit gates, I'm just also doing a couple of 2 qubits and 3 qubit gates, but it's all done at once. Is this still something that people care about?
This is it. I guess you can do a little bit of this, but but only a very little bit of this. So the way I'm using transversal, it's saying that I'm only touching 1 qubit from each block.
Yeah.
At a time. I mean, I can do many things in parallel, but it's always of a tensor product of a bunch of things, and it's not ever doing an entangling operation between different qubits in the same code block.
Yeah.
Because this will kill your distance very quickly.
Right. Okay.
But I think like if you have a high distance, if you do a little
partition
bit,
of qubits, you can do that without killing your distance too much.
If
You
you have
don't
what?
mix and match. If you do CZ and then you don't do another CZ between other.
right? Like if you sort of
Right.
split it into
Yeah.
groups or something, and you say, well, inside of these groups,
I can do, so
yeah,
that
nice.
may not kill your distance too much, but probably is a bit more complex because which partition do you try? So which partition it's easier
Yeah,
to find the matrix itself. But otherwise, if I tell you, okay, group your qubits in two pairs. Like if you have 15 qubits, you have to try your
which is a
what
good
are you gonna-
grouping to get nice transversal things. It's an exponential search space, I guess, for this kind of.
I think if you start allowing for different partitions, you want even to go beyond even having a partition. Historically, I think people were considering what they called locality preserving unitary implementations of logical gates. That means you have a logical gate that even though there is no tensor product decomposition as like a unitary, say, you can still give a bound on the weight of the operators, right? So it has bounded spread, inspired by some light cone arguments and so on. And you can also show the existence about these in like certain spatial dimensions. But this, I think.
Do you know why people don't really talk about these?
I mean,
Is it just because it's very
call-
complicated for
So-
threshold theorems or something,
Yeah.
once you have these things.
The tricky part is, I think, the decoding, because before people were thinking about practical decoders, people, I've seen the term fault tolerant logical gates as meaning exactly that. You can bound the weight of any error that goes in, and then you have a code family, and for each instance of that code family, you have a unitary implementation such that its depth doesn't scale with the size of the code family. And then people say, that's fault tolerant, and then statements about this. But it's much harder to actually deal with than this if you have a partition.
Right.
So yeah, my understanding was that like there was a sense that if you wanted to universal computation, you would need something like log D depth anyways to touch all the qubits, and then kind of the no-go proofs like Easton Kernel, they kind of apply if you have a tensor product, and it's hard to deal with these circuits. That was kind of my sense of why. You already have the graphically bound, right? That kind of deals with these locality preserving unitaries, right?
That's exactly where they were invented. I think also.
The what bound?
The graphically, like it's like for topological codes, they say that in, I'm sure you heard of it. It's like in D dimensions, you can only do logical operations, and with constant depth circuits, you can only do like logical operations that are in the Tth level of the fire.
Okay, yeah.
So I haven't heard of this. What is the Brownie sample?
Graphically.
And
It's
then
called classification of, I forget the rest of these.
and Yoshida Paslavsky have a follow-up,
Yeah, the
which is nicer to read, I find.
It depends, yeah, I mean, both are nice, they're nice. No, it's called the disjointness.
So this is like what people used to argue that I need like a 3D surface code to have a transversal T or something like that.
But I had actually a question about what you said before, I didn't catch about the acting on different code blocks, transversal between different code blocks. So, if I have like a situation where I have two different code blocks and I want to apply, let's say, or maybe not C not, like something non-Clifford, like C, controlled something that's non-Clifford. Can I represent it also like this in the same notation?
Yeah, so
Does it have like the same nice form?
yeah, so what would that look like? I think it would look like one of these kinds of things.
Yeah.
So you can imagine here I've got my sort of my pi by 4, my bold dot kind of coming at the input, and then I have an arrow, which is a matrix. And then I'm sort of splitting the wires into 2 code blocks, and I'm saying act on 2 code blocks. But then that matrix, I should put some restriction on what kind of matrix that is to say that it's acting transversally.
But then wouldn't that, I thought that, maybe I probably just can't read the calculus well enough. Wouldn't that mean that you'd act with single qubit unitaries on each of the?
No, so if I well, yeah, I don't know if I can draw on this thing, but if I,
In theory, yeah, try it.
if I, will it just,
I'm not an expert.
will it just work?
Anyone know how
You
it's
might have to click like the annotate button on this, right on the top. There's like one of the annotates, like on the Zoom. bar.
Yeah, up,
Is it like here?
yes.
That one.
Annotate.
I don't know if it works.
Oh, no, because it's on my computer.
Yeah.
Yeah, because I can't.
If you
but-
press annotate.
I press annotate.
No, this is the screen sharing.
Yeah, but that's like when you just annotate on the screen.
Yeah, but whoever's.
Yeah,
anyway.
Yeah, I mean, I can annotate on my screen, and actually that might be good enough. So let's see. So if I sort of if I put the arrow there, right, and this is a matrix. The touchpad, this is fun. Oh, a circle. There we go. Pi by 4 is what this squiggly means. Then this A is going to be able to have so I want to make a restriction on A that's more general than saying that I have to have unit vectors in every row. I want to say it's of a block form where each of the blocks is a unit vector. Okay.
Oh, I see. In the T case that you showed before, it wasn't just any matrix, it was a matrix where you had this restriction that.
Yeah, on the physical side, that was how you would impose the transversal restriction, is I would say that my rows are unit vectors. Here I could say that my rows, I can sort of split my row into 2. And I have a unit vector sort of on both sides of the line. And that's like saying I'm just touching 1 qubit from each of the blocks. But then I think the condition looks exactly the same. It's just putting a different restriction on the matrix.
Yeah, I see.
And if you did tweak around with conditions on P, do all the algorithmic stuff, does that still go through? If I, fix H and LNS and I weaken the restrictions on P, can I still use the same procedure to find P if it exists? Does the Hamming wave thing play a big role?
I would expect so. So the way that you would find a P, it's a little bit non-trivial. I mean, the naive thing you could do is you could just look for all the P's, that would work, right? But that's not very good. And this is this tri-orthogonality is a nonlinear condition. So you're not just solving a linear system, but there's a way that you can pose this as solving a system of equations over Z8, over the ring Z8. And there's ways you can do this in ring theory sort of efficiently. They use it's a generalization of the Gauss-Jordan form called something with an H, like Howell, using Howell normal forms of matrices. It's very weird because you can have pivots sort of appear and disappear and stuff, because this is because you have 0 divisors in your ring now, so it becomes like quite complicated. You're looking at PCDs and stuff, but you can do it efficiently.
Yeah, okay, so the weight one thing doesn't play big.
So yeah, it's not too difficult because you're basically just saying, let me just figure out how many, the power of all of my T gates, right? So that's a number from 0 to 7. So I'm just trying to solve for this vector of powers. I think if you go to multiple blocks, it's still going to be easy, but that's something that would want to be sort of worked through, or easy, as efficient as the other one.
Yeah. Cool.